All right, let's start today with a scenario that I think is going to feel, well, uncomfortably familiar to a lot of our listeners, especially if you're, working the line at an OEM or staring at quality reports at a tier one supplier.
The dreaded Monday morning meeting.
Exactly. Picture this. You are on the assembly line. The specs say every single bolt in the chassis was tightened to exactly 100 Newton meters. The digital torque wrench clicked. The lights on the tool turned green. The data log says, pass.
On paper.
On paper, you have built a perfect, safe vehicle.
But then what happens?
3 months later, you get a field report. A critical joint came loose. Or, even worse, a bolt snapped under load. And you were sitting there staring at the data thinking, how is this physically possible? We did everything right. The tool said it was tight.
That is the nightmare scenario. And honestly, it's a nightmare caused by what we call the torque lie.
The torque lie. That sounds a bit dramatic, doesn't it? Like some kind of conspiracy theory. But looking at our source material today, it seems like we have been operating on a fundamental misunderstanding of physics for, a century?
It's not so much a misunderstanding as it is a convenient approximation that we've just outgrown. Today, we are doing a deep dive into the 2026 Master White Paper from NedschroefNedsonic Holding BV.
And the technology in question is Nedsonic. Now, before you tune out thinking this is just an ad for a new screw, stick with us. This is actually a look at how the industry is shifting from, guessing a bolt is tight to knowing it is tight.
Right. It's the shift from indirect estimation to direct measurement.
So if you are an engineer dealing with tighter tolerances in EVs, or you're a buyer terrified of the costs of a recall, this is your wake-up call. Let's start with the problem. I think most people, even car enthusiasts, assume that torque equals tightness. If I crank the wrench hard, the parts are clamped together hard. Why is that wrong?
Because torque is just effort. It's rotational force. It's how hard you are sweating to turn the wrench.
Oh.
Tension or preload, that's the actual clamping force holding the wheel on or the engine mount together. And they are not the same thing.
But surely they are related. I mean, if I apply more torque, I get more tension.
In a perfect world, yes. But we don't live in a perfect world. We live in a world with friction. There is a rule of thumb in engineering, often called the 50-40-10 rule.
Okay, walk me through that.
So when you apply torque to a bolt, you are inputting energy. But about 50% of that energy is lost immediately, just overcoming the friction between the bolt head and the surface it's sitting on.
Wait, 50%, so half my effort is wasted before I even start turning the threads.
Gone, just creating heat. Then another 40% is lost to friction inside the threads themselves, the steel rubbing against steel.
Yeah, 50 plus 40, that leaves 10.
Exactly. Only about 10% of the force you apply actually goes into stretching the bolt and creating that clamping force.
That seems incredibly inefficient. We are basing the safety of a vehicle on a process that is 90% waste.
It is inefficient. But the inefficiency isn't even the main problem. The problem is that the friction isn't constant. We call it the variable.
Explain that. What changes it?
Everything. Imagine a drop of oil gets on the threads where it shouldn't be. Or the coating thickness on the bolt is slightly off. Or, and this happens all the time, the temperature in the factory shifts by 10 degrees between the morning shift and the night shift.
And that changes the friction.
Drastically. Let's say the friction drops because of that oil. You apply the same torque, the wrench clicks at the same spot, but because there was less resistance, you've actually over-tightened the bolt. Maybe you've stretched it right to the breaking point.
And the tool still says green light.
Correct. Or the opposite. A bit of dust or rust increases friction. The wrench clicks, thinking it's done its job, but all that energy went into fighting the rust. You have almost zero clamp load. The bolt is loose, but the computer says it's tight.
That is terrifying. Basically, the tool is telling you it did its job, but it has no idea if the bolt did its job.
Precisely. And in a world of self-driving cars and high-torque electric motors, hoping the friction was consistent isn't a strategy, it's a liability.
Okay, so that's the invisible problem. So enter the solution. Nedsonic. The white paper makes a pretty bold claim. It says they turn the hardware, the bolt itself, into a sensor. How do we go from a dumb piece of steel to a smart sensor?
We stop looking at the wrench. We ignore the input entirely. Instead, we measure the physical length of the bolt while it's installed using ultrasonics.
Ultrasonics, like checking for a cracked pipe or a medical ultrasound?
Similar concept, but we use what's called the time-of-flight principle. Imagine you are standing at the edge of a canyon and you shout. You wait for the echo. If you know the speed of sound and you measure the time it takes for the echo to return, You can calculate the distance to the canyon wall perfectly.
Okay, I follow the analogy.
Nedsonic does this inside the bolt. A transducer sends a very short ultrasonic pulse into the head of the bolt. That sound wave travels down the shaft, hits the end of the bolt, and bounces back
And the system times it.
with micrometer accuracy. Now, here is the physics. Hooke's law. When you tighten a bolt, you are stretching it. You are pulling the steel apart like a very, very stiff spring.
So a tightened bolt is physically longer than a loose one.
Yes. And as it gets longer, the path for that sound wave gets longer. So the time of flight increases. By comparing the time of flight of the loose bolt versus the tightened bolt, the system calculates exactly how much the bolt has stretched.
And since we know the properties of steel,
Elongation equals preload. It's a direct, linear relationship. There is no guessing about friction. We don't care if the threads are oily or dry or the temperature changed. We are measuring the actual physical result.
that is a fundamental shift. You are verifying the outcome.
Correct. The bolt itself tells you how tight it is.
But I have to play the skeptic here for a minute.
Go for it.
This sounds great in a laboratory with, white coats, but automotive factories are noisy, dirty, chaotic places. Can you really shoot sound waves through a bolt on a moving assembly line and get a reliable reading?
That is a valid concern, and that's why the white paper spends a lot of time on the hardware. You can't just grab a rusty bolt from a bucket and do this. To make a bolt a Nedsonic bolt, there are specific design requirements.
What kind of requirements? Are we talking about expensive, exotic materials?
No, standard steel grades. But the geometry matters. Section 4.2 of the paper details this. First, look at the head of the bolt. It has to be manufactured perfectly flat.
Why flat? Does the shape of the head really matter that much?
It matters for acoustic coupling. You need a clean contact patch for the sensor to send that pulse. If the head is concave or has a raised manufacturer's logo in the center, you get air gaps.
And sound doesn't like air gaps.
Sound hates traveling from the sensor through air into steel and back. It just scrambles the signal. You need a smooth landing pad.
Okay, that makes sense. What about the other end, the tip?
That's even more critical. They need a reflection surface. If the end of the bolt is jagged or uneven, like a sheared cut, the sound wave scatters. It's like looking in a broken mirror. You need a sharp geometric transition at the tip to bounce that signal back cleanly.
So it creates a clear echo.
Exactly. And the white paper also notes that you ideally want an external drive, like a hex head, rather than an internal socket. You need enough solid metal thickness at the bottom of the head to let the sound wave propagate correctly without interference.
So for the manufacturing engineers listening, this does require a spec change. You have to order the right bolt.
Yes, but once you have that verified geometry, the system is incredibly robust. The paper talks about ultrasonic stiffness, or KUS. Once you calibrate the system for a specific bolt and clamping length, it is stable. As long as you don't stretch the bolt until it permanently deforms, which means you've ruined the joint anyway, that measurement holds up.
You mentioned robust. I think engineers get nervous about new tech. They don't want to be the guinea pig for some beta test.
And they shouldn't be. But here's the thing. Nedsonic isn't new. It's just becoming available to the wider market. The white paper drops a massive anchor case study here. DF trucks.
Trucks are a great test case. High vibration, heavy loads, millions of miles. If it breaks there.
DF has been using this technology in series production for over 25 years.
25 years, so this isn't a pilot program.
No, it is their standard operating procedure. They use it on all engine bolts and all chassis joints. The paper says Nedsonic is their first diagnostic instrument whenever a process deviation occurs.
That's interesting phrasing. First diagnostic instrument.
Think about what usually happens when a bolt fails on the line. The line stops. Everyone panics. They grab a torque wrench and check the other bolts. Click, click. They seem tight. But are they?
They don't know. They're just checking the friction again.
Exactly. DF doesn't do that. They grab the Nedsonic unit, they touch the bolt head, and instantly they know. This bolt has 40 kilonewtons of clamp load. This one has 20. No guessing. They can instantly see if it's a tool issue, a part issue, or an operator issue.
But that speed of diagnosis must be worth a fortune in downtime prevention.
It's invaluable. And it's not just DF. The white paper lists a who's who of OEMs. Schmidt's Cargo Bull uses it on heavy-duty trailer kingpins. That's a massive M14 bolt. Mercedes uses it on the A-class rear axle and truck bumper mountings. BMW uses it for yield-controlled applications.
Yield control.
That's when you tighten the bolt so much it actually starts to stretch permanently. It's a very secure way to join things, but the torque curve flattens out, so a torque wrench effectively becomes blind. Ultrasonics is one of the only ways to verify those joints non-destructively.
So the technology is battle-tested, it works, but I want to pivot to the business side. We have listeners who are buyers or purchasing managers. They are hearing custom bolt, flathead, special reflection surface, and they are seeing dollar signs.
And that's a fair reaction. The white paper acknowledges there is a limited premium on the bolt cost. It's not a commodity bin part anymore.
So how do you sell that to a CFO? Hey, I want to spend more money on screws.
You have to look at the insurance logic. You have to zoom out. What is the actual cost of a bolt? 50 cents, a dollar.
Sure.
In that range.
Now, what is the cost of a recall on a steering column or a brake caliper coming loose on the highway?
Millions. Maybe tens of millions.
Yeah.
Plus the brand reputation damage, which you can't even quantify.
Exactly. If you are buying bolts for a non-critical application holding on a plastic trim piece, fine, buy the cheapest commodity fastener you can find. But for safety-critical joints, the premium for a Nedsonic bolt is pennies compared to the risk exposure. It is cheap insurance.
That's risk mitigation.
It's also about the cost of poor quality, or COPQ. We've all been in those meetings where a joint fails and the finger pointing starts. The bolt supplier says, my steel is good. The coder says, my friction is within spec. The tool guy says, my robot is calibrated. And meanwhile, the production line is stopped, burning cash every minute.
Nedsonic cuts through that noise, gives an objective, physical answer. The bolt is only stretched 50%. Okay, now we know the clamp load is low. Why? We can investigate. It turns a week-long investigation into a 5-minute check.
There's also an angle here for the suppliers listening, the sales managers trying to sell fasteners to these OEMs.
Huge opportunity. If you can walk into an OEM and say, I'm not just selling you a bolt, I'm selling you traceability, I'm selling you a guarantee that you can verify this joint for the life of the vehicle, that is a massive differentiator. You aren't competing on price anymore. You're competing on process security.
Traceability is a buzzword, but this makes it real.
It does. And looking forward, this is only going to get more relevant. The white paper has a really interesting section at the end, section 11, about the future roadmap. They call it NedTight meets Nedsonic.
NedTight is their thread-forming bolt, right? The ones that cut their own threads as you drive them in.
Correct. Manufacturers love them because you don't have to tap the hole first. It saves a step, reduces debris. But think about the friction. You are physically deforming metal as you drive that bolt. The torque required just to cut the thread is huge and incredibly variable.
So the torque reading tells you basically nothing about how tight the joint actually is.
Right. You might be using 90% of your torque just to cut the thread and almost nothing to clamp the part. It's the ultimate guessing game.
But if you combine that with ultrasonic...
Exactly. You get the efficiency of thread forming, no tapping, but you use Nedsonic to verify the final preload. You check the stretch. It solves the biggest weakness of thread-forming fasteners.
That seems like a game changer for things like battery packs or these new mega castings we're seeing.
That's the context we need to leave the listeners with. Look at how cars are changing. We are moving to EVs. We are casting entire rear chassis sections in one piece of aluminum.
If you strip a thread in a mega casting, you haven't just ruined a bracket. You've ruined a massive, expensive component.
Exactly. And with battery packs, structural rigidity is everything. You cannot afford to have bolts rattling loose inside a high-voltage pack. The margin for error is disappearing.
So direct verification isn't just a nice-to-have feature anymore. It's becoming a necessity.
It is. We are moving from an era of trust to an era of proof.
That's a powerful way to put it. I want to leave our listeners, the engineers, the buyers, the sales managers, with a thought to chew on. Next time you're walking the line or signing off on a PPAP for a safety-critical joint, ask yourself this question.
What's the question?
If your family was going to be in that car driving at 70 miles an hour, would you be comfortable relying on a torque wrench's prediction based on friction? Or would you want a measurement based on physics?
When you put it that way, there's only one answer.
There certainly is. Thanks for taking this deep dive with us.
Pleasure to be here.